Jeanie McKean Test on Gerard Morin Pole Transformers Over-Unity AC Circuit Analysis, presented by Tim Lee, April 2018. My name is Tim Lee. I am 66 years old, living in Singapore. I am a retired engineer, experienced in electromechanical repair and maintenance of steam sterilization equipment in hospitals. I wish to share with the knowledge seekers that I did an AC circuit analysis to add on the knowledge to extend my understanding of the Jeanie McKean test on Gerard Morin pole transformers over unity circuit. The test on Gerard Morin pole transformers over unity circuit consists of two pole transformers in cascade connection, one 25 kVA, the other 15 kVA capacity, both rated at 14,400 volts. It was experimentally demonstrated that with a 3,600 watt petrol-run electric generator, supply 120 volt, 60 Hz, 30 ampere, it could support 6.8 kilowatt of heater appliances. Source: Gerard Morin's transformer replication. Concepts: the AC circuit analysis is done by applying concepts of ideal transformers, voltage source, current sources in modeling the circuit. Ideal transformers, their VA capacities are conserved in the cores without power loss, so that the VA in the primary winding equals VA in the secondary winding. V in, A in equal to V out times A out. Voltage sources. Their internal resistance are infinitively high, so that they do not take any current across. To measure the voltages, I equal to V over R in equal to 0, or R in equal to infinity. Current sources. Their internal resistances are 0, so that they do not take any voltage across. To measure the current, V equal to I times R in equal to 0, R in equal to 0. The E3600 electric generator. This means the E3600 can generate 3,600 watt, equal to 3.6 kilowatt. The mechanical energy that is convertible to electrical energy equal to 3.6 kilowatt, equal to 3,600 VA. When this electrical energy is input into the 25 kVA pole transformer at 120 volt, its available current is 3,600 VA divided by 120 volt equal to 30 ampere. Note: electric power equal to V times I times cosine theta equal to VA. Resistive load cosine 0 equal to 1. Theta is the phase angle between voltage V and current I. Voltage is Newton meter per coulomb. Ampere is coulomb per second. The coulomb terms got cancelled out in the multiplication. Generally speaking, VA is the energy capacity. KW is the Power consumption. VA and watt are of the same dimensional units. Newton meter per second. Kilogram times meter per second square times meter per second. mL square T minus 3. The load. 2 heat radiators equal to 2 times 1500 equal to 3000 watt. 1 saw cutter equal to 1500 watt. 1 impact drill equal to 800 watt. 1 drill equal to 800 watt. 1 grinder equal to 700 watt. Total power demand equal to 3000 plus 1500 plus 800 plus 800 plus 700 equal to 6800 watt. Power RL equal to 6.8 kilowatt at 120 volt. RL equal to 120 square divided by 6800 equal to 2.1176 ohm. Current IRL equal to 120 divided by 2.1176 equal to 56.6679 ampere. Power P equal to I square R equal to V divided by R square times R equal to V square divided by R. R equal to V square divided by P. The input transformer capacity is 25 kVA. This means it can take up to 25 kVA from the electric pole. It can supply up to 25,000 VA divided by 120 volt equal to 208.3333 ampere at 120 volt output. Likewise, 25,000 VA divided by 14,400 volt equal to 1.736 ampere at 14,400 volt input. X2 equal to 120 divided by 25,000 divided by 120 equal to 0.276 ohm on the low voltage side. X1 equal to 14,400 divided by 25,000 divided by 14,400 equal to 8,294.4 ohm on the high voltage side. In this circuit, the 25 kVA transformer is run reversed. The input is connected to the low voltage side at 120 volt AC from the generator. So the high voltage side, it is by induction from the input 120 volt AC. The output would depend on its turn ratio, N equal to 120, as given by the step-up transformer formula. V out equal to N times V in. Step down, V in divided by V out equal to N. 14,400 divided by 120 equal to 120 equal to N. Therefore, its maximum induced high voltage V1 equal to 120 times 120 equal to 14,400 volt AC or 14.4 kV as rated. The output transformer capacity is 15 kVA. This means it can take up to 15 kVA from the electric pole. It can supply up to 15,000 VA divided by 120 volt equal to 125 ampere at 120 volt output. Likewise, 15,000 divided by 14,400 equal to 1.04167 ampere at 14,400 volt input. X4 equal to 120 divided by 15,000 divided by 120 equal to 0.96 ohm at the low voltage side. X3 equal to 14,400 divided by 15,000 divided by 14,400 equal to 13,824 ohm on the high voltage side. In this circuit, the transformer is run forward. The input is connected to the high voltage side at induced V1 equal to V3 equal to 14,400 volt AC. This high voltage is stepped down by the transformer into low voltage. V in divided by N equal to 14,400 divided by 120 equal to 120 volt. The Gerard Morin pole transformers over-unity circuit. It consists of two pole transformers in cascade connection. The input Vi is connected to 120 volt AC generator. Vi equal to 120 volt. The output Vout is connected to 120 volt AC load. Vout equal to 120 volt. In between, the high voltage coils are connected in parallel with the blue lines in the circuit. I shall now replace the primary and the secondary coils with their resistances, calculated as above. 25 kVA, X2 equal to 120 divided by 25,000 divided by 120 equal to 0.576 ohm on the low voltage side. X1 equal to 14,400 divided by 25,000 divided by 14,400 equal to 6,294.4 ohm. 15 kVA, X4 equal to 120 divided by 15,000 divided by 120 equal to 0.96 ohm on the low voltage side. X3 equal to 14,400 divided by 15,000 divided by 14,400 equal to 13,824 ohm on the high voltage side. The input circuit from the electric generator, 3,600 watt equal to 3,600 VA. The current I equal to 3,600 VA divided by 120 volt equal to 30 ampere. The 25 kVA pole transformer has very low resistance. X2 equal to 0.576 ohm. It can take up to 208.333 ampere as rated. Hence, it is not a problem to take in 30 ampere. The input current from the generator is limited by its power. When the 3,600 watt is fully converted into electricity, the mechanical energy convertible to electrical is 3600 VA calculated above. These 30 ampere shall consume energy in X2 as 30 squared times 0.576 equal to 518.4 VA. The cascaded circuit. The secondary second transformer is connected by the red line. V1 and V3 are the same. V1 equal to V3 equal to 14,400 volt AC. When 30 ampere current from the 3600 watt generator is fed into the 25 kVA transformer, its input energy equal to 30 times 120 equal to 3600 VA. X1 and X3 are connected in parallel. The combined resistance is X1 parallel X3 equal to X1 times X3 divided by X1 plus X3 equal to 8,294.4 times 13,824 divided by 8,294.4 plus 13,824 equal to 8,294.4 times 13,824 divided by 22,118.4 equal to 5,184 ohm. Total current I1 transferable from the generator to X1 parallel X3 equal to 3600 VA divided by 14,400 volt equal to 0.25 ampere. The power consumption in the cascade circuit equal to total current square times X1 parallel X3 equal to 0.25 square times 5,184 equal to 324 watt equal to 324 VA. The output circuit. The secondary transformer 15 kVA is run normal, step down. Open circuit response. When the load is not connected, off. The VA consumption accounted for in X1 parallel X3 to the 15 kVA output transformer equal to consumption in X1 parallel X3 plus consumption in X2 equal to 324 plus 518 equal to 842 VA. The output current in the 15 kVA transformer IX4 equal to 842 divided by 120 equal to 7.0167 ampere at low load. Open circuit current. This is the leakage current at X4 required to maintain 120 volt output. This IX4 equal to 7.0167 ampere shall have power consumption in X4 equal to 7.0167 square times 0.96 equal to 47.2647 VA. This 47.2647 VA shall be accounted for in the total current in X1 parallel X3 when the load is on. The output circuit. Load response. When the 6,800 watt heaters drills are connected on. the load RL equal to 120 square divided by 6,800 equal to 2.1176 ohm. Current IRL equal to 6,800 divided by 120 equal to 56.6667 ampere. Total current required I/O equal to IRL plus IX4 equal to 56.6667 plus 7.0167 equal to 63.6834 ampere. VA required in X4 to support the load equal to 120 times 63.6834 equal to 7,642 VA. Total current I1 required in X1 parallel X3 to support the load equal to 7,642 divided by 14,400 equal to 0.5307 ampere. This total current I1 is now become a demand in the cascade circuit X1 parallel X3 equal to 5,184 ohm. The power consumption in the cascade circuit is the total current square times X1 parallel X3 equal to 0.5307 square times 5,184 equal to 1,460 VA. This power consumption in the X1 parallel X3 cascade circuit shall effect a demand in X2. IX2 equal to 1,460 VA divided by 120 volt equal to 12.1670 ampere. Cascade to input circuit. This IX2 equal to 12.671 ampere reflect back from the X1 parallel X3 circuit. It shall consume energy in the 50 kVA transformer X2. 12.671 square times 0.576 equal to 92.4792 VA. Total energy required from the generator to support the 6,800 watt load equal to X1 parallel X3 consumption plus X2 consumption equal to 1,460 plus 92.4792 equal to 1,552.4792 VA. This 1,552.4792 VA is equivalent to total demand in X2. 1,552.4792 VA divided by 120 volt equal to 12.9373 ampere. Current amplification equal to output demand divided by input demand equal to 56.667 divided by 12.9373 equal to 4.38 over unity. VA equal to 1,552.4792 4792 VA divided by 646 equal to 2.08 horsepower. This indicated that 2.08 horsepower is sufficient to support the load at 6,800 watt. Continue simulation. 1.5 loading response. Since the above calculation indicated only 1,552 watt was consumed, there are energy available to support a larger load. I continue this AC circuit analysis with larger simulated load. This factor of 1.5 times the loading is obtained by repeated calculation with 2.25, 2. and 1.5. When the loading is 1.5 times 6,800 times 1.5 equal to 10.2 kilowatt. Current demand from the load RL equal to 10,200 divided by 120 equal to 85 ampere, and the generator is unchanged at 3,600 watt or 4.825 horsepower, 30 ampere. Open circuit. When the load is not connected, off. The output current that is transferable in X3 from the 3,600 watt generator equal to 30 ampere calculated above. The output current in the 25 kVA transformer IX4 equal to 7.0167 ampere at low load open circuit current. This is also the current at X4 required to maintain 120 volt output. 1.5 closed circuit response. When the load RL is on, total current required I1 equal to IRL plus IX4 equal to 85 plus 7.0167 equal to 92.0167 ampere. VA required in X4 to support a 1.5 load equal to 92.0167 times 120 equal to 11,042 VA. The current I1 required in X1 parallel X3 to support the 1.5 load equal to 11,042 divided by 14,400 volt equal to 0.7668 ampere. This I1 equal to 0.7668 ampere is total current required to support the 1.5 load at 10.2 kilowatt with 3,600 watt generator. This total current I1 equal to 0.7668 ampere shall demand in the cascaded circuit X1 parallel X3 equal to 0.668 square times 5,184 equal to 3,048.1 VA. This 3,048.1 VA shall demand in the 25 kVA transformer back to the input at X2. 3048.1 VA divided by 120 volt equal to 25.4 ampere. This 25.4 ampere shall consume in X2. 25.4 square times 0.576 equal to 371.6365 VA. Total consumption in X2 equal to 3048.1 plus 371.6365 equal to 3419.7366 VA. These 3419.7366 VA divided by 120 volt equal to 28.4978 ampere, equivalent to 3419.7366 divided by 746 equal to 4.5 horsepower. This calculation indicated that the 3600 watt 4.8 horsepower generator is sufficient to support up to 10.2 kilowatt loading. It shall require 28.4978 ampere, and the 30 ampere fuse shall not be blown. This VA 3419.7366 divided by 120 equal to 28.4978 ampere is within the capacity of the 50 kVA pole transformer. Current amplification equal to 85 divided by 28.4978 equal to 2.9827 over unity at 8.5 kilowatt load. Note: 1.5 times loading at 10.2 kilowatt, the generator required shall be 4.5 horsepower. It cannot go higher loading with 4.85 horsepower already. The 30 ampere fuse shall be at the verge of being blown. In conventional measurement, as long as the generator is running, it is always producing that 30 ampere at 120 volt. It keeps the current flowing. If no consumption, the generator's engine will run easier. So it could be current amplification equal to 85 divided by 30 equal to 2.8333. And the previous calculation could be 56.667 divided by 30 equal to 1.8889. Short circuit response full load. When the 6.8 kilowatt load is short circuited, it shall demand full load current at the output X4. On the 15 kVA transformer, its full load current I4 equal to 15,000 divided by 120 equal to 125 ampere on the low voltage side. This total current I0 equal to IRL plus IX4 equal to 125 plus 7.0167 equal to 132.0167 ampere shall demand on the Cascade circuit X1 parallel X3 equal to 132.0167 times 120 divided by 14,400 equal to 1.1 ampere. 1.1 square times 5,184 equal to 6,272.64 VA divided by 120 volt equal to 52.272 ampere. This 52.272 ampere demand, when reflected back to input from its generator, it shall consume energy at X2. 52.272 square times 0.576 equal to 1,573.84 VA. This total VA required from the generator equal to 6,272.64 plus 1,573.84 equal to 7,846.48 VA. This 7,846.48 VA divided by 120 volt equal to 65.3873 ampere. This indicated a 65 ampere circuit breaker CB1 shall be installed for 25 kVA pole transformer production. Short circuit response, full load. Current amplification equal to 125 divided by 65.3873 equal to 1.9117 over unity at full load. This shall require a generator of 65.3873 times 120 equal to 7,846.476 watt equal to 7,846.476 divided by 746 equal to 10.518 horsepower. A 10.518 horsepower equal to 7,846.476 watt generator. It shall affect the open circuit current IX4 at X4 and the VA consumption in X2. So I need to calculate again to make sure the demand is within 10.5 horsepower. Calculate 10.5 horsepower again. The total current I1 transferable from a 10.5 horsepower generator equal to 7,846.476 divided by 14,400 equal to 0.5449 ampere. This current I1 equal 0.5449 ampere shall consume in X1 parallel X3 equal to 0.5449 square times 5,184 equal to 1,539.1796 VA. The open circuit, when the load is not connected off, the VA that is transferable in X1 parallel X3 to the 15 kVA transformer to X4 equal to 1,539.1796 VA. The output current in the 25 kVA transformer IX4 equal to 1,539.1795 divided by 120 equal to 12.5 8265 ampere at low open circuit. This is also the current at X4 required to maintain 120 volt output. When the load RL is short-circuited, full load current 125 ampere is on. Total current demand on the full load I/O equal to 125 plus 12.8265 equal to 137.8265 ampere. VA required in X4 to support 137.8265 ampere equal to 137.8265 times 120 equal to 16,539.18 VA. The current required in X1 parallel X3 to support 137.8265 ampere equal to 16,539.18 divided by 14,400 equal to 1.1486 ampere. This 1.1486 ampere created consumption in X1 parallel X3 equal to 1.1486 square times 5,184 equal to 6,839.1577 VA. This 6,839.1577 VA created demand at X2 equal to 6,839.1577 divided by 120 equal to 56.9930 ampere. This 56.9930 ampere demand shall consume energy in X2 equal to 56.9930 square times 0.576 equal to 1,870.9644 VA. The total energy required from the generator equal to 6,839.1577 plus 1,870.9644 equal to 8,710.1221 VA. 8,710.1221 VA is also 8,700.1221 watt equal to 11.6758 horsepower. This indicated that the generator is to be settled between 10.5 horsepower to 12 horsepower. Is sufficient to cover the full load. The short circuit loading 125 ampere. When the generator is upgraded to 12 horsepower, the 15 kVA would have overloaded and may even burn out. The generator should stop at 10.5 horsepower. 8,710.1221 divided by 120 equal to 72.5844 ampere. Current amplification equal to 125 divided by 72.5844 equal to 1.7221 over unity at short circuit overload. To avoid power trip, 125 ampere circuit breaker CB2 for the 15 kVA pole transformer protection is to be installed. Summary: the Jeanie McKean test covered pole transformers combination 25 kVA to 15 kVA, current amplification 4.38, generator 4.825 horsepower, generator 3.6 kilowatt, load 6.8 kilowatt, maximum load 10.2 kilowatt, current amplification 2.9827, full load output 125 ampere, current amplification 1.9117, generator required 10.5 horsepower, circuit breaker CB1 65 ampere, circuit breaker CB2 125 ampere. The pole transformer 25 kVA X1 equal to 8494.4 ohm, X2 equal to 0.576 ohm. For the 15 kVA, X3 equal to 13,824 ohm, X4 equal to 0.96 ohm, X1 parallel X3 equal to 5184 ohm. Appendix: current amplification. As shown in this AC circuit analysis, it indicated that the Gerard Morin Over-Unity was achieved in the Cascade circuit by X1 parallel X3, which lowered the resistance to 5,184 ohm. Also, the voltage being stepped up to 14,400 volt reduced the total current in X1 parallel X3. The VA consumption, total current squared times X1 parallel X3 is reduced. It gives more current available from the generator to support a larger load. As calculated in previous slides, the VA required in the input to Cascade to output are respectively 1,552.4792 VA to 1,460 VA to 7,060.42 VA with 3,600 watt generator, 6,800 watt load. Conservation of energy. In a step-up transformer, as in the 25 kVA pole transformer, being run in reverse, there is current amplification because of its turn ratio N. In a step-up transformer, the energy capacity VA has conserved. VA times A1 times A in equal to V out times A out equal to N times V in times A out equal to 120 times V in times A out, imply that V in equal to 120 A out. V in as a common factor got cancelled out, resulting A in can amplify A out by N equal to 120 times. Conversely, changes in the A out only required change 1 over N in A in. Current distribution in X1 parallel X3. In this AC circuit analysis, I take I1 as the total current in X1 parallel X3. Since X1 parallel X3 equal to X1 times X3 divided by X1 plus X3, I1 equal to V divided by X1 times X3 divided by X1 plus X3. The current into X1 is Ix1 equal to V divided by X1. From I1, V divided by X1 equal to I1 times X3 divided by X1 plus X3, imply that Ix1 equal to total current times X3 divided by X1 plus X3. Likewise, the current in X3 is Ix3 equal to V divided by X3. From I1, V divided by X3 equal to I1 times X1 divided by X3 plus X1. Imply that Ix3 equal to total current times X1 divided by X1 plus X3. The use of these equations, Ix1 and Ix3, are physically related to the current flow in the high voltage side of each pole transformer, 25 kVA and 15 kVA. When adding up Ix1 squared times X1 plus Ix3 squared times X3 equal to total current squared times X1 parallel X3, the result shall be the same. VA in output. In the output, I put VA times ampere equal to VA required. A 6,800 watt load at 120 volt required IRL equal to 6,800 VA divided by 120 volt equal to 56.6667 ampere. In open circuit, the leakage current is to maintain 120 volt. Ix4 equal to 7.0167 ampere. Total current to support the load IO equal to IRL plus Ix4 equal to 56.6667 plus 7.0167 equal to 63.6834 ampere. VA required equal to 120 times 64.6834 equal to 7,642.008 VA. RL equal to 120 square divided by 6,800 equal to 2.1176 ohm. X4 equal to 0.96 ohm. VA required equal to 56.6667 square times 2.1176 plus 7.0167 times 120 equal to 6,799.8569 plus 842.004 equal to 7,641.8609 VA. This indicated that 7.0167 ampere is used to maintain 120 volt. 7.0167 squared times 0.96 equal to 47.2647 VA. Their total consumption 6,799.8569 plus 47.2647 equal to 6,847.1216 VA would be a smaller value. Conclusion. In this AC circuit analysis, it is indicated that there is current amplification 4.38 over unity at 6.8 kilowatt load due to reduced consumption in X1 parallel X3. In one-pole transformer 50 kVA, there is step-up voltage amplification from 120 volt to high voltage 14,400 volt. The other pole transformer 25 kVA, there is step-down voltage suppression 14,400 volt to 120 volt. By cascading two pieces pole transformers 25 kVA to 15 kVA, the total VA consumption VA equal to 525.4559 VA equal to 525.4559 divided by 746 equal to 0.7044 horsepower within the 4 horsepower generator's capacity. 2,980 VA. This explained why the generator's 30 ampere fuse was not blown. At 1.5 times loading, 10.2 kilowatt, the current amplification falls to 2.9827. The 3,600 watt generator is sufficient to support the 10.2 kilowatt load. The short circuit response indicated that at 15 kVA full load, 125 ampere, the current amplification falls to 1.9117, and the generators need to increase to 10.5 horsepower to support the full load output to load at 125 ampere, equal to 125 times 120 equal to 15,000 VA, as the 15,000 VA pole transformer rated. The low voltage input on the 25 kVA, it has low resistance, X2 equal to 0.576 ohm. It can easily take in high current, have high current surge. It can lead to power trip. It is not suitable to plug in to the wall socket. 65 ampere circuit breaker CB1 to be installed for 3,600 watt 4.85 horsepower generator protection to limit at short circuit loading 125 ampere. 125 ampere circuit breaker CB2 to be installed for RL overload protection. The generator has limited current supply. It separates the circuit from the electric grid. Unchecked short circuit, unchecked loading, it can lead to power trip. The 25 kVA can overload the 15 kVA, lead to burnout of pole transformers. Installation site for the pole transformers is to be on plinth, high position, in room, lock up, accessible to authorized maintenance personnel. The 14,400 volt wiring, even the neutral return wire in the circuit, when inadvertently shortened to ground, it can lead to electric sparks hazard. The wiring termination screws, nuts are to be tightened for good conduction of electric current to avoid arcing. The pole transformers are to be isolated from the ground with high voltage 20,000 volt insulation mat. This AC circuit analysis is based on theoretical simulated loads. I have not done tests to verify to validate the result. Caution: high voltage 14,400 volt is known to produce electric sparks touching metal surfaces and earthing to earth ground. Caution must be taken. Do not touch any of the wiring in the circuit. Check all wiring terminations, screws tightened, wires securely fastened, cables properly insulated prior to power on. To prevent electrical arcing, prevent current leakage. The pole transformers must have labeled high voltage 14,400 volt AC to alert end users. Insulation site to be on plinth, high position, 20,000 volt insulation mat, lock-in room with high voltage 14,400 volt sign. Testing, servicing, repair, maintenance to be done by experienced, qualified personnel. Keep out of children, keep out of aerosol, flammable items away from the test site, test benches. Take same precautions as we would for any electrical appliances. Thank you for watching. This completes my presentation. I wish this presentation to be useful to the knowledge seekers, electrical engineers, students, researchers, for continued research, for practical use of the circuit. Thank you, Gerard Morin, for the knowledge on pole transformers over unity circuit. Thank you, Jeanie McKean. Thank you, Skip. Thank you, Jim. Thank you, YouTube. Thank you, knowledge seekers. Thank you, my wife, Doris. Have a good day. Peace to the world.